Good evening and welcome to Tinkering with Edkelar. For this episode, I got something slightly different than usual. A project update report of sorts. Normally, I'll try to keep projects together in one video, or at least in several parts together. But this 9825A thingy keeps popping up in my thoughts, and I keep getting the weirdest ideas for what to do with and around it. And I'm not even remotely done yet. So far, however, most of the project is software related, so please excuse the abundance of screen captures this time. So, what have I been up to? Let's have a look. First sub-project, the RAM modules. As I said in the original project series, the RAM boards I got all had their issues. And I just so made one of them work. There was a bad trace for data bit 6 on it, hence the botch wire. It does work, but occasionally the system fails to boot, and I also keep getting error 14, which translates to program structure destroyed. These odd errors at odd times make me think that the RAM is anything but reliable. So, let's make a drop-in replacement with newer components. I started off by looking at the reverse engineered schematics by Tony Duell. Sorry if I butchered that pronunciation. And I also used the HP patent and CPU documentation, which both contain some timing diagrams. Original HP schematics are only around for the CPU board itself. All of them can be found on Curious Mark's HP9825 website. Here's what I found out. The memory bus side of the device contains the tri-stated IDA bus lines for the main data transfer. IDA stands for Instruction, Data and Address. That hints to the fact that this is a multiplexed bus that contains the address in one state and then the data or instructions in another. That complicates things a bit. The next interesting signal is called STM, which is Start Memory. It signals the beginning and end of a memory access cycle, both read and write, and for both ROM and RAM. Note that just about all signals are active low, which makes it a bit harder to wrap your head around them at times. The STM signal from the CPU is actually split into two signals also, STM and STM-ROM. The ROM version is tied to the clock and thus a bit delayed. Anyhow, the border between the ROM and RAM area can be set with two dip switches on the CPU PCB, and it will only affect the other split signal. I can't fully read the name of either of these, but the signals are there to send the ROM units the final Put Data on the Bus Now signal. This is essentially the output enable signal for the selected memory chips. Overlapping RAM and ROM regions might clash for that reason, since RAM doesn't care about that switch. Next we have the WRIT line to indicate write access. Like usual RAM system, this differentiates read from write access. And almost done, there is a line labeled MEB, which I guess is memory busy. It gets signaled when the RAM isn't ready to complete the requested read or write due to a refresh cycle in progress. The last line is called byte. If it is signaled, the CPU wants the upper or lower 8 bits of the addressed words only, depending on the A15 address bit. For the reads, this can be ignored since the CPU only takes what it wants anyway, but for writes, it would destroy half the word in RAM with random data if you don't honor it. Now the RAM PCBs are available as 8K and 16K modules. Same thing in general, only double the chips and a few more address selection circuits. I'll use the 8K one as a template. As you can see here, the RAM chips used are DRAMs, and those require a refresh, which is implemented in pure TTL on these boards. Also, these types of chips are pretty early DRAMs and have a chip select line that requires a 12-volt pulse, whereas all the other signals are TTL levels. And to top it off, they have an input and an output pin, which are inverted to one another. So you store a low on an address and it gets read back as a high. There is an inverting buffer for the output section in it for that reason. Oof, complicated. But then I thought, it's just 32K of RAM, or 2 times 16K chips for these at maximum. Why even bother to use DRAM? Back in the day, SRAM of that size might have been too expensive and power hungry, but modern chips? Surely a few SRAM chips would be easier to implement, no refresh cycle needed, and modern chips have 5 volts all around and no inversion on the data. I could ditch about half the circuitry. I did a quick search on eBay to find dip-cased SRAM chips with parallel bus pins. Those are rare these days. Most new SRAM is either serially connected or surface mounted. Also, the 9825 runs at 6 MHz, so it has to be able to cope with that. A single RAM cycle does have several clock cycles for the bus multiplexing, but the times to enable the output still have to cope with the single clock. What I found was a set of TC55328-20 chips. 20 nanosecond access time is plenty fast, and it's a 32K SRAM chip, so double what I actually would need. Timing seems reasonably well suited, and the signaling between chip enabled, output enabled and write control seems to be a good match for what I need. I first made a KiCAD symbol for that chip. Oh, KiCAD. Is anybody else annoyed with their handling of power supply pins? These always take up way too much space on the schematic, no matter if they are directly attached to the chip's symbol or have a distinct unit for them. Has anybody ever thought about a power connection table solution instead? Sort of a background spreadsheet where all the ICs have their power pins listed and you can just connect them all to VCC or ground with 1 or 2 mouse clicks. I mean, why even bother with these obvious connections in the schematic itself? It can be printed in a table output anyhow if needed for reference. Just an idea. Okay, here we go. I need the PCB connector, which needs a matching footprint, also handmade. Next, I need some address decoding. I'll use the same chips as the original as much as possible. Note that the 9825 has the RAM region in the upper address space and the ROM in the lower. Thus, the top 8 kilobytes always need to be RAM, but below that, it's optional. I decided to put in a set of dip switches to configure 8 kilobyte blocks to add for all 4 configurations that were available: 8, 16, 24 and 32 kilobytes of RAM. There are some ROM expansions that cut into that 32K range and wouldn't be compatible, so I'll mostly use the 24 kilobyte option. Oh, the decoder chip is open collector, so a simple pull-up based electrical OR will do the trick. Next, I need an address latch. Since I don't have a refresh circuit, quite a few chips can be omitted already. The STM signal gets inverted and makes for the ALE signal that other CPUs have, address latch enabled. The CPU has the address in question on the IDA bus when STM goes low, so that is the perfect time to capture and hold that. The memory busy signal got driven from the refresh logic in the original. Since I'm removing that part, I'm simulating it with the delay line that is needed for the write access. This is the one part I'm not 100% sure about. Maybe it could be completely removed, but that is an experiment for later. The chip enable lines can be driven from the combined byte and A15 signals. Turns out that the required signaling is a bit more complicated though. I had to add the card enabled signal into the mix too. Output enabled reacts to the latched card enabled and read now signals from the CPU board. The data bits can be connected directly to the IDA bus. As long as the bits get faithfully stored, it doesn't matter if a true is a low or the other way around. No inverter needed, and since there should only be the CPU as a receiver, no driver required either. Now, this circuit is too far removed from the original for me to blindly make a PCB for it. So I started off by breadboarding a model. Just to validate the concept and maybe get a few successful I/O cycles in the logic tracer. At 6 MHz, I don't expect it to actually work like that. To make the task a bit easier, I ordered the updated version of the system ROM PCB along with a little breakout PCB to plug into the memory bus without a ton of grabber clips, including printed labels for the signal names. But it did work in the end. Woohoo! Well, admittedly, I had to tweak the circuit a bit. The chip select logic only got the extension for the card enabled line during testing, and the delay line was a bit off. Way too much negative logic in this thing for my taste. So, next step. Making the PCB. Again, it took a bit of arranging items. And after a bit of soldering fun, I can plug in the new RAM PCB. Turn on. Yes! Success! And after configuring everything for the 24 kilobytes of RAM, the list command agrees. I got over 20 kilobytes of available RAM. Strike! And here's another KiCAD gripe. I need mounting holes in here for very specific locations, so I add them from the footprint library. No problem. But when I update the PCB from the schematic, they get nixed because they aren't part of the schematic. Ah! So to prevent that happening a second time, I deselected the Remove Unused Components option, and that led to an unused chip being left on the design. Sheesh! KiCAD, it would be nice to have a flag unused component option instead of removing them. That way I could see which ones I have to delete myself, or keep if I choose to. The second part of the update is about future hardware tinkering. The strength of the 9825 are the expansion slots for different I/O solutions. But of course, there are no new ones coming out from HP anymore. So, how about making your own? Seems easy enough. There is the I/O bus, some read-write and status lines, And even the address lines aren't multiplexed here, since it's only 4 bits for 16 devices total. But making the prototype and debugging the circuitry does require access to the card while the system is running, and the I/O slots are recessed. Originally, HP had a test adapter or I/O extender card. That was a pass-through card that plugs into the I/O slot and allows the I/O card to be connected outside the base unit. Notice that the extender is at a 90-degree angle, so it is even easier to access the card and still have access to the base unit's keyboard. Nice, I'll take that. Now, just connecting the two card edge connectors in a 1-to-1 scheme seems a bit boring. What features can I add? Oh, how about a pin header too? So I can easier hook up the logic analyzer? Yes. And jumpers to selectively connect or disconnect a signal? Also a useful feature. I could have used dip switches, but the jumpers double as additional connection points for measuring. Oh, and what if something fails? How about fuses in the supply voltage lines? Yes. And lastly, the ground planes of the cards are usually connected to the earth pin of the extender, not regular ground. I don't know if that's universally so, hence I make it an option. And tada! The outlines took a bit of measuring and estimation time, but here we are. I put the jumpers into grouped positions. 5 volt and ground here, 12 volt and earth down there. Connection points for the voltage rails have both pre and post jumpers labeled in and out connection points over here. If you pull the jumper, you can use these for current measuring, for example. The pin header fits nicely on the edge. I kept the same layout of pins as the bus connector for simplicity. Oh, and I also labeled all of the connections, so poking something with a logic probe should be less pin counting than normally. The data bus jumpers are one big block, and the control lines are grouped by topic: IRQ related items, addressing, reset, status, I/O control, and DMA. The prototype PCB arrived and soldering begins. I also created an OpenSCAD model for the case based on the original extension module housings. The extension card has an open end and holes for the fuses, but upcoming possible new modules should also get a nice case. Oh, and there is a little foot on the HP version to avoid sagging when the I/O card is inserted. I also made a little bracket for that. After testing with a homemade 3D printed case, I decided to get a custom printed one. Much smoother than I could have done. Now the hardware prototyping can begin. Or can it? The next idea also led to the one following it. Do you see a pattern? Talk about rabbit holes. Anyhow, HP provided a real-time clock module. Curious Mark has a few repair videos for that on his channel. Check them out for details beyond my ramblings here. When I looked for some, I found an eBay offer for over $400 plus shipping. Yikes! That is a good chunk of what I paid for the base unit. No way I'm shelling out that much just to keep the time. But the service manual has the schematics. After having a good long look at the schematics, I thought, can't be that hard to remake one of these with some glue logic for the bus communication and an 80 mega chip for the microcontroller, as well as a modern RTC chip for the clock circuits. But what I also noticed was, the bus interface between the I/O cards and the base unit has to follow several common rules. So the interfacing logic is pretty much duplicated in all the I/O cards. Now when I want to breadboard an idea, I don't want to rebuild all the same base circuitry every single time. So how about I make a generic adapter and breadboarding interface. What does the adapter need? The bus connector? Check. Address decoding? Check. Based on the model number, I even found a new old stock of the original rotary encoder. The two IC signals decode to the I/O registers. The CPU calls them R4 to R7 respectively, and the decoder will provide a direct input or output lines for each of them. Check. The interrupt handling requires priority resolution. If the card wants to interrupt the CPU, it sets the request line, either the high or low priority one, depending on the I/O address. After that, the CPU will interrogate the cards and ask for the matching data line to be pulled low. That way, the CPU can find the highest priority device, even if all of them request an interrupt at the same time. All of this has to be baked into the addressing circuitry. Check. Flag and status lines are to be set whenever the card is selected. Check. And finally, the 9825 uses the second I/O register, R5, as a status and a command register by convention. All high-level commands map to that. RDS, read status, will read R5, and WTC, write command, will write to it. While the basic I/O is 16-bit capable, all the interfaces I've seen so far only use the lower 8 bits connected to the status and command info. I'm following that pattern for simplicity and provide latches and bus transceivers to write or read those bits as needed. Lastly, a generous pin header for interfacing. And a prototype PCB, of course. The form factor has to fit into the I/O card slots, so it's a bit cramped. I have soldered stuff to the prototype, but the actual in-depth testing has to wait a bit because my initial testing got cut short by the error 14 issue again. This is when I realized that the source of the problem might not have been the RAM after all. The error 14 issue goes away as soon as I remove the I/O option ROM card. Yikes! Can it be that the old ROM chips are having thermal issues? It's repeatable. Power on a new day, it works. And once it stops working and gives the error 14, it will do so until the I/O ROM is removed. Then it works fine again. There is a slim chance that something is wrong that only gets triggered when the I/O ROM is active, but since the I/O bus is working fine even with the error 14, keyboard, tape and printer work flawlessly, I think the ROM is the reasonable assumption. And that brings me to the next sub-project, a generic ROM replacement card. The physical ROM modules are getting rare and apparently also prone to failure. My system ROM had a completely broken chip, for example. Now each original ROM contained a single expansion in a fixed address space. Over time, HP provided combination ROMs like Basic and Advanced I/O in one module. The 9825B moved all of the ROMs into the machine to begin with, but I'd like to keep the charm of the A model going, and so I came to the conclusion, let's learn the art of making ROM cartridges and forge a single one to contain all the ROMs. One cartridge to rule them all. Like the RAM, the original way back ROMs had a 12-volt enable line and thus were a bit power hungry. Modern ROMs, both E and EEPROMs, should be just fine as a replacement. I need some that are larger than 2K or 4K, but still have parallel I/O. The smallest ones I could find here are 64 kilobyte ROMs. Plenty of space. What we need is, like with the RAM, an address latch. Check. Next, we need an address decoder circuit. Since we know what range the ROMs can be, we can decode any of these addresses and provide dip switches to select which block to enable or disable. Oh, and since I have more than double of what I need in space, I can use one bit of the ROM address space to have a bank selection, allowing two sets of ROM images in the EEPROMs without reprogramming them. Now that minimalist circuitry still needs to fit into that ROM drawer of the 9825A, which has even less space for it than you'd think, because the pull handle takes up a chunk on the inside. I had to discover the change side option in KiCAD to go double-sided with the chips and also make this my first 4-layer PCB to get everything into that small space. The soldering is a carefully planned sequence since some parts will obscure other solder pads. Oh, and the pins need to be clipped tightly. This stack-up is designed to the fraction of a millimeter. And here's where the postal services fails me. I'm still waiting for the 8-bit latches that make up the address latch. They are overdue by a week already. And that brings us to the pure software side of things. Back when I was working on the system ROM replacement, I thought, it would be nice to have an assembler or disassembler for the images, just to see if and where there might be trouble. And so I sat down and started writing one. Nothing too fancy, mind you, just a quick and dirty implementation that did the job. And, do you know the term feature creep? By now, I brushed up the assembler part to the point where it should support all the mnemonics of the original one, including some macro-style commands and listing output control. My first test case of this was a RAM checker. At that time, I still suspected the RAM to be the culprit of my unstable system. To truly and thoroughly test the RAM, one has to do it in situ though. It's not good to test it with an external system or adapter. Those will not stress the RAM chips in exactly the same way. And so, I wrote a bit of assembler code for the CPU that could be put into the system ROM as a drop-in replacement. It should exercise the RAM by writing and reading back different patterns and also somehow report back the results. Seems easy enough. Until you realize you have to make all of this work without using any RAM at all. Because it's sus. And that complicates things slightly. But here's what I got. First, the boot code starts at 40, all addresses are in octal as per convention, and I mimic the boot jump code that the original ROM does. Then I declare a few useful constants, and the bit patterns to use for the RAM checks. Now here's where I fell into a trap first. The CPU has a weird indirect addressing mode, which will check the highest bit of the read data, and if it is set, it will use the lower 15 bits as the next indirect address. So it automatically follows a chain of pointers to pointers. But since my test patterns do want to change the highest bit too, whoops, I had to split them into bytes instead. So 2 bytes, only the lower 8 bits of each word, make up the real test pattern for the case. Add a few text message constants, and then we start. Get the reset button flag from the keyboard and jump to the hot or cold boot. Not much of a difference here, I just wanted to see if it works. I used just another welcome message to differentiate. Now the RAM check starts immediately by turning on the run light via the subroutine run on. But wait, calling a subroutine? Without RAM? Where does the return address go? Ha! I found a hack for that. Normally, the call stack register R for the stack pointer points to the memory region. But this CPU uses memory addressed registers. Hence the first 32 bytes are actually in CPU register addresses. And one of them is a forward long floating point register, AR2, but since I don't want to use floating points, I just let the return stack use these 4 words. So I have an in-CPU 4-level deep call stack. Just enough for comfy programming. All of the other variables that I need, like the current block, found failed bits, current pattern and so on, are distributed over the other registers. For example, I don't use interrupts, so I can use the interrupt vector for the current block address, even though that register doesn't have all the 16 bits available. And so, the memory test runs through the entire RAM space, and ROM, be careful to pull those out before running, and reports the failed bits in a string of marks on the printer, one for each memory block. So by counting the lines and columns of the failed bits, you know pretty much exactly where the fault is. Now the next big question that kept nagging my noggin was, how can I streamline debugging of the RAM checker code? I mean, I'm pretty sure I know what I'm doing, but mistakes, especially in assembly level on a completely new system, aren't an option, they are the norm. And so, I decided to go one step further with my assembler and disassembler project. What I have here is a simulation of the CPU inside the 9825. Since the entire unit is pretty much the CPU with a few attached I/O devices, RAM and ROM, I was confident that I could get a reasonable result. But boy did I not see how deep that rabbit hole can go. I had to pretty much code each and every instruction of the CPU. From simple ones like load AB from or compare AB to more complex ones like EXE, which executes a command within a memory location. Sort of an eval equivalent for you JavaScript folk. And sometime along that line I decided to also implement cycle counting based on the timing info in the CPU specs. So each command computes how long it took in CPU cycles. Combine that with the clock frequency and we can tell how long the device has been running. Adding a memory manager object on the side that takes care of splitting RAM, ROM or unavailable regions and can also insert memory errors, it should work. Instead of hard coding the output to the CPU directly, I created I/O devices and basically connected them via the same logic with the CPU as the real devices would have to follow. Here I coded up a version of the KDP, which includes key presses to trigger an interrupt and provide the pressed key upon request. Enough feature creep already? No? Good, cause I'm not done yet. To visualize the output on the screen, I decided to pick up an old project of mine, a console UI library similar to the old school TurboVision that was popular in DOS times. It's not quite done yet, it lacks quite a few components, but it does the job for a quick and dirty debug session, simulating input for my CPU simulator and producing legible output. Yay! Since the CPU simulator is contained in the library, I thought it might be possible to create a non-console application host for it eventually. And here I got worried about the optics of it. The font for the display and the printer is identical, they both use the same character ROM. But it's a very distinct 5x7 pixel matrix font. And so, deeper the rabbit hole goes. I made myself a font creation program that takes the text file as an input with the pixel info and outputs an SVG format. Why SVG? Because it's easy to create from scratch. And then a quick call to FontForge later, ready-made TTF and WOFF2 fonts. Combined with the simulator created HTML printout, I think that looks pretty snazzy. Oh, and remember that real-time clock I/O card? Well, I started on that one too. And it does work almost completely already. The simulated version, that is. I'm able to read the current time, set the current time, and even start and stop the timer channels that it offers. What's missing here is the interrupt integration and the factory internal commands. Thanks to Mark and Ken, and unbeknownst to me at first, the firmware code is available. I worked from the manual and schematics myself, but having the internal commands also functioning seems a good idea for a reproduction. Link in the description. The last bit that I'm currently still working on is the tape drive. And boy, that is a tough nut to crack. Some control signals around it derive from the tape movement sensor, the tachometer, and some are purely time-based. Between the HP patent and the service manual, I got pretty far along and can already rewind a blank tape, mark files on the tape, read and write files on the tape. That is to say, I'm almost done already. What's missing is the DMA integrated search feature and a way to actually modify the tape images. And that's it for this update to the 9825 project. Even though it was a bit more on the abstract and talkative side, I still hope you enjoyed my research. See you next time! My first test case. The soldering is thus a carefully planned sequence, since some plants, yes of course, plants. It's 420, why am I thinking of plants?